This mini lecture will introduce the periodic table, how it is organized, and the regions that mark groups of elements with similar properties. First, let me comment on the fact that introducing the table at this point is always a bit tricky, as the organization of the elements really all comes down to electrons, which we won't be talking about in detail until chapter 4. But as I'm sure some of you will remember some of these concepts from your previous experience with chemistry, I'll make a few comments now about this, and we'll discuss this again in chapter 4, so don't worry if you're too confused about some of my conversations about electrons over the next few slides. Basically, it all comes down to the fact that the table is structured around the valence orbitals that contain the electrons in the atom that will be involved in bonding. There are 4 different types of electron orbitals labeled S, P, D, and F. And as you can see by the way the table is colored on this slide, specific columns of the tables correspond to these specific electron orbital shapes. Additionally, the periods or rows in the periodic table roughly correspond to the energy levels of the electrons in these orbitals. The reason that the elements are organized by electron orbitals is because the electron configurations of the elements dictate the properties of the element. So certain groups of elements will have similarities in their electron configurations and therefore similar properties. Note that this version of the table that we have on this slide now has an expanded color scheme that really highlights elements with similar properties, which we will discuss over the next few slides. Most of the elements in the periodic table are metals, and they break down into several categories. The first column is called the alkali metals, and the second column is called the alkaline earth metals. The large green D block in the middle of the table represents the transition metals, which contain some common coinage metals and some jewelry metals that you are probably familiar with. The elements in this particular block of the periodic table have some really unique properties and are actually kind of complicated, and so they're the focus of an entire upper level subtopic called inorganic chemistry, which happens to be my particular area of expertise. All the metals in the table share similar properties that I've listed on the left, but they're not crucial to memorize, except, most importantly, metals tend to give away some electrons and therefore exist as cations in chemical compounds. Again, more on this later. This represents a picture of potassium, so we can see that sort of shiny metallic color that we're getting for this metal. Same thing with magnesium here. You'll notice it looks very shiny, very metallic. And of course, copper, which we're very familiar with, which also is very shiny. And it also displays some of these interesting properties over here that we typically have for metals. We know that copper, it's used for conducting electricity. It's also very easy to flatten into thin sheets. It's easy to stretch into a wire. So copper is like really a good example of utilizing these properties in a way that helps with a lot of infrastructure that we have. The upper right corner of the table contains the nonmetals, which are the primary focus of organic chemistry, and we'll also spend a lot of time working with them in general chemistry. Nonmetals also share the properties listed on the left, and most importantly, nonmetals tend to gain electrons and therefore exist as anions in chemical compounds. Again, a couple pictures for examples here. Carbon, here we can see there's 2 forms of carbon. I've kind of hinted at this before, that diamonds are composed entirely of carbon. And we also have graphite, which is also composed entirely of carbon. Now, you may be wondering why these 2 things look so different, and it all comes down to crystal structures. So carbon has a very ordered and very compact crystal structure. It's one of the hardest materials because of how long the carbon has been compressed in order to reach this very, very rigid and very structured crystal structure. Whereas graphite, while it also has a very ordered structure, it actually has sheets for its structure. And so those individual sheets are able to kind of slip and slide past each other, which is why graphite is commonly used for things like pencils, because it rubs off really easily. It transfers like a powder very easily due to the slippery sheets that its crystal structure will form. This yellow compound here is sulfur, so we can clearly see this is an example of one of the brightly colored substances, and that, none of these really specifically look metallic, although I would say graphite can kind of appear to look a little shiny at times. And then finally, iodine actually is purple in color when it's a solid, and it also has this unique property of very quickly turning into a gas at room temperature. So iodine will exist as a solid, but it can also sublimate very easily if it's just warmed just slightly to form a gas. The last column of the table contains a uniquely stable set of elements referred to as the noble gases. And this is because they have a special electron configuration that is particularly desirable. And we'll talk more about this later. But in fact, all the other elements in the table are trying to gain or lose electrons in an effort to achieve the same number of electrons as one of these noble gases. And so this is a really important column of elements to pay close attention to. Again, we'll get a better explanation of this in chapter 4 and 5. Here's some examples of the noble gases. These are commonly used in fluorescence tubes. So the color that you get from various different types of fluorescent tubes often comes from the type of gas that's contained in the tube. And we get this fluorescence by applying an electric current across the gas to excite the atoms, which then leads to them emitting photons. And their colors actually particularly line up with the electronic structure in these atoms. Again, we'll talk more about this in chapter 4. Now, on either side of this diagonal line that separates the metals from the nonmetals, we have a group of special elements that are referred to as the semimetals or sometimes as metalloids. And these elements share properties of both metals and nonmetals, as I've got listed on the left over here. And several textbooks actually have different interpretations of exactly which of these elements are truly in between a metal and a nonmetal. And that's partially because they behave a little differently depending on the other atoms they're interacting with when they're forming chemical compounds. So that can always make this a little confusing. If we note here what these look like, despite the fact that they're poor conductors and they're very brittle, just like most of the other nonmetals, we can see that they often look very metallic and kind of silvery. And so that's one of the reasons why they fall in this sort of in-between category. Finally, just a brief note on the groups notation that's often found above each column in the table. The A groups that we have listed here are often called the main group elements, and they're really the primary focus of this introduction to chemistry that we're going to get in general chemistry classes like the one we're in, Chem 121, and the one that a lot of you will probably take next semester, which is 122. Note that there are 8 of these columns in the A groups, and so they're numbered where they kind of skip over this middle block and pick up again where it left off. So you go 1, 2, and then 3 through 8. And this number 8 is really important because we're going to tie this back into electron configurations when we get to chapter 4. So pay attention to that. The B groups contain the transition metals in the middle of the table in this green block, as well as the lanthanides and actinides series, which actually is technically supposed to be inserted into the periodic table at this position, which makes the periodic table twice as long. So one of the reasons we often include it below the table is really just so that the periodic table fits on like a normal size sheet of paper. And you don't need to use some sort of long piece of paper to represent the full table. So it's important to note here that this block in purple is actually inserted in between the orange and the green blocks, almost just like how the green block kind of gets inserted in between the orange and the blue blocks that we see here. Now, these B groups are really, again, they have unique properties from the main group elements, and so they're really the focus of another class, but we will work with many of the elements in the first row of the green block and some of the others that are kind of interspersed throughout here. So you will see some of these elements, but we won't really get into the nitty-gritty of their special properties in this class. So, this concludes the 4th and final mini lecture for chapter 2. Please note any questions you may have about this material and how it is utilized to solve problems in the sapling homework or end of chapter exercises for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our virtual class meetings, and during that time, we'll focus more on problem solving for concepts in this chapter.